We have one video this week on proofs, and I'll just be honest, mentally, this is probably the hardest thing we're doing conceptually so far in the course, perhaps even in the entire course. We're going to talk a little bit about logical equivalence at the end too, but we're not covering all the slides in this lecture. We don't need to. We're just going to briefly touch on some stuff. And basically whatever we cover in this video, we're going to use. Everything we don't cover, it's just there for your information. So, indirect proofs. We've done these things called direct proofs so far in the course. So when we do set laws, we're doing direct proofs. When we do truth tables and we're showing something as a tautology, a contradiction, it's a method of a direct proof because we're taking a definition, we're applying some rules or steps to it, and we're getting a result. But if we have a well-formed formula that has, like, say, more than two variables, like let's say we have a well-formed formula with like 5 different propositions, we're going to get a truth table with 32 rows. So to figure out if a truth table with 32 rows is a tautology, a contradiction, or contingent, it takes a lot of time. It is, in fact, a waste of time to do it by hand. A computer should be doing it, but there's another alternative method that we can use to figure these things out, and this is called a proof by contradiction. So I'm going to run through the general strategy, then I'm going to show you proof by contradiction for tautologies, contradictions, and entailments, and we'll do an example of each. And the first time you do this, it will be rough. That's okay. There's practice that you can do. And if you understand the truth tables, and you really understand the truth tables, then most of these things should follow. If you're still hazy about some of the directions that we're going through during this video, then you might want to spend a little bit more time with the truth tables or have them nearby so that way you can understand exactly what's happening. Well, I shouldn't say understand what's happening, but be able to reference and visualize what's happening with the truth tables. So here's the idea for a proof by contradiction. Let's say we have a fact. Alpha is a tautology. Well, we could either show that it's true in every single row, or we could just try to create a row that's false. And when we try to create a row that's false for a tautology, well, we're going to find that's impossible for it to happen. We'll find a contradiction somewhere. So because it would be impossible to create a row that is false, we know that every row has to be true. And this is sort of the idea for a proof by contradiction. So whatever statement alpha we want to prove, we just assume its negation is true. So we assume not alpha is true. And what we're going to find is that we're going to find a beta that's true, and we're going to find not beta that's true. So basically, if we assume not alpha is true, we're going to get a contradiction at some point. Now, because we get a contradiction, we know that not alpha cannot be true. Alpha has to be true, because we shouldn't get a contradiction from anything. Now, this is just the general idea of things. I'd rather do it with an actual example and go through it because I think it makes more sense to use actual examples. But with a proof by contradiction, essentially what we're doing is we're assuming the opposite. We're showing it's impossible for the opposite to be true. Therefore, our initial assumption is false, and whatever we have, like alpha on its own, should be true. Anyways, let's show that P or not P is a tautology. So, a P or not P is a tautology. This is really easy to do in a truth table. We would find that there's 2 rows and they both come out to 1. But instead what we're doing, and I'm going to draw a syntactic tree for this, we have P or not P. In fact, let me just draw it in black. P or not P. That's going to split into P, and not P will split into the negation in P. Okay, so if it's a tautology, every row should equal 1. So what we're going to do, and I'm going to do this with a truth tree first on the right, and I'm going to explain it in words after on the left. Let's just assume this is false. So we're going to assume that there is a false row. In other words, we're going to try to force a row to be false and show that it's impossible to force it to be false. Okay, if P or not P is false, what does that mean? It means by our truth table, we have to have 0 or 0, because that's the only time when the or is false. So this means that P is false and not P is false. Now, what happens with not P? Well, we have to negate 0. So not 0, when you negate it, gives us 1, right? So this means that if not P is 0, then P is 1. Now here we have a problem. Our problem is we've now found out that P is both false and true at the exact same time. In order to force a row in P or not P to be false, so P or not P is 0, to force that row, we get a contradiction. We get P is false and we get P is true at the exact same time. This is impossible. We cannot have a single proposition that is both true and false simultaneously. Therefore, this assumption that P or not P can be false is totally wrong. This must be true. So because it must be true, we know it's a tautology. So I'm going to do the same proof with words. Okay, so with words, and I'm going to clean up this mess a little bit over here. Try to just get rid of the blue marks, so that way we can sort of see the tree. Okay, so what we do is we first assume, because we want to prove a tautology, we're going to assume the opposite. Assume that P or not P in some situation V. So this V just means a particular situation, or you can think of it as in a particular row. Write out the O a little bit more clearly. Assume that for some particular row, it's false. Now, since P or not P is false, so this was the first line here. This one shows us that first step. Since P or not P is false, we know that P is false and not P is false by the semantics of the disjunction. So this gives us this second tier in our truth tree. Now, since we know that not P is false, we must have that P is true by the semantics of the negation. So this corresponds to this last tier in our tree. And now at this point, we have a contradiction. Since in line 2, we found that P is true, and in line 3, we found that P is true. Sorry, in line 2, we found P is false. In line 3, we found P is true. So it's 0 in line 2, it's 1 in line 3, and this is impossible. Therefore, our assumption in line 1 is incorrect. It cannot be 0 in any particular situation or row. Therefore, P or not P is true, and we should say in every single row or every situation. So that proves that it's a tautology. So again, with proof by contradiction, we assume the opposite. If we want to prove it's a tautology, we assume, hey, it's not a tautology. Let's find the row that's false. Let's force it to be false. Oh no, we forced it to be false. Now we run into a contradiction somewhere. It is impossible to force that row to be false. Therefore, it has to be true. So I want you to try this example on your own, showing that P arrow Q arrow P is a tautology. So pause the video, try it, and I will go through the solution right now. So first, I want to do the same thing I did before. I want to do a truth tree first. I want to talk through it with the truth tree, and then I will talk through it with the actual proof itself in words. So we want to show this is a tautology. So the first step we're doing, in fact, let's just write this out simultaneously. I'm going to assume that P arrow Q arrow P in some situation is false. So I'm going to specifically write for some V. In other words, we're assuming in some situation it's false. We're going to force it to be false. So this is like giving a 0 to P arrow Q arrow P. Now, what do we know about the conditional with its truth values? When is it false? It's only false when we have 1 arrow 0. So this means that P is going to be true, and this means that Q arrow P is going to be false. So 2, so we know by the semantics of the conditional, we're going to have that P is true and Q arrow P is false for that situation. And that's because 1 arrow 0 is only false when the antecedent is true and the consequent is false. Okay, we're going to do the same thing on Q arrow P now. So Q arrow P, when is that false? It's true when the antecedent, or it's false when the antecedent is true and the consequent is false. So we should have Q equals 1, and we should have P equals 0, and that makes the conditional false. So in step 3, same reasoning by the semantics of the conditional, we know that Q is true, and we know that P is false. Okay, at this point, we have a contradiction. Where's our contradiction? Well, what do we have here? We have P is true, and we have P false at the same time. So P is true, and P is false. Therefore, our assumption is incorrect, and P or not P is true in every row. Okay, so basically, because we found our contradiction here, P is 1, P is 0 at the same time, we know our initial assumption cannot be true. This has to be true. This has to be 1. Basically, we forced P arrow Q arrow P to be false. We found that if we force it to be false, we run into a contradiction. Therefore, it cannot be false in any situation. It has to be true in every situation. Therefore, it's a tautology. So the first time you see this, yeah, this is going to be tough to do. It's going to be tough to do on your own. But as you do more examples, you get more comfortable with it. Let's see what happens with contradictions. So I want to show that P and not P is a contradiction using an indirect proof. So let's just draw the truth tree for this, P and not P. This is going to break up into P and then not P, and then not P is going to break up into not and P. So a contradiction is 0 in every situation, in every row. So what we're going to do is we're going to say, hold on, let's force this to be true and see what happens. Okay, so this is our first step. We're going to assume that P and not P is true for some situation V. Now, if P and not P is true, well, let's ask ourselves, when is the conjunction true? It's true when both of the conjuncts are true. So this means that P is true, and this means that not P is true. So this is our second row here. Since P and not P is true, both P is true and not P is true by the semantics of the conjunction. Now, we can do the same thing here. If not P is true, then we know that P has to be false. So this is the third row here. Since not P is true, we must have P is false, and this is due to the semantics of the negation. If something is not true, then it has to be false. So now we have a contradiction. We have P is true, we have P is false. Therefore, we know our initial assumption is not true. It is impossible to construct a row where P and not P is true because we end up with a contradiction. Therefore, our initial assumption is incorrect. P and not P must be false in every single row. Therefore, this has to be a contradiction. Because it's false in every single row. So it's the same idea as the tautology proof. We assume the opposite. We show it's impossible to have the opposite happen. Therefore, it must be a contradiction. So here's another example. Show that not P arrow P is a contradiction. Pause the video, try it yourself, and I will give you the solutions now. So let's just draw a truth tree for this, and then we'll do the thing in words. Okay. So when you write your proofs, do it in words. I'm using the truth trees to help illustrate the process. Okay, so we're showing it's a contradiction, so we assume the opposite. We're going to force it to be true. So step 1 is assume that not P arrow P is true for some situation V. Okay, so what does this mean? If not P arrow P is true, that means that P arrow P is false. So by the negation, we have that P arrow P is false. Okay, so again, think about the truth table for P arrow P. When is it false? It's going to be false if we have 1 arrow 0. So this means that P has to be true, and then the consequent P has to be false. So 3, we can say by the conditional, we know that P is true, and we know that P is false. Oh, okay, so here's our contradiction. P is true, P is false at the same time. These both cannot happen. So contradiction based on line 3. Therefore, our assumption is incorrect. Our assumption that we can have a true row is wrong. It must be false in every row. Therefore, we can say that not P arrow P is false for every row V. And therefore, we know that this well-formed formula is a contradiction. So we just changed it into words. I am shorthanding the proof a little bit, but even by shorthanding this, I'm still explaining all my steps. So if you shorthand it like I did on the left, I don't mind. If you do it for someone else, you might want to be a little bit more formal. But for me, this gives me the same information as writing it in full sentences would. So for instance, we assume it's true for some situation. Negation shows us that P arrow P is false. The arrow shows us that P is true and P is false. Here's our contradiction. Therefore, we know that not P arrow P is false for every situation. Therefore, we have a contradiction. Okay, so that's indirect proofs for tautologies and contradictions. Let's now think about proofs for entailments, and we have one example that I've gone through. So, entailment. Remember, if A entails B, so if alpha entails beta, what this just means is that alpha arrow beta is a tautology. Okay, so what this means is that if alpha arrow beta is a tautology, when we do a proof by contradiction, what we do is we just assume that alpha arrow beta is false. For some situation V, we show that's impossible. So this should give us an impossibility. And therefore, we're going to find that alpha arrow beta is going to be true for every situation V. Okay, so entailment is really just the same thing as an indirect proof for a tautology, because entailments can be represented by tautologies. So it's just sort of one extra step of interpreting what entailment means and putting it into a form that should be a tautology, and then doing a proof by contradiction for a tautology. So here's the example. We want to show that P and P arrow Q entails Q. So we can put this in tautology form. So this would be P and P arrow Q entails Q. So I'm going to draw the syntactic tree for this. This splits up into Q and P arrow Q. I'm not going to draw the operators in the tree just because it makes it a little bit more crowded. This will split up into P and P arrow Q, and then P arrow Q splits up into P and Q. Okay, so if this is an entailment, this woof should be a tautology, which means every row should be true. So what we're going to do is we're going to assume it's false. So that's step one. Let's assume that is false. So what this means is that we're going to have 1 arrow 0. So P and P arrow Q will be true, and Q will be false. That's our assumption. So by the semantics of the conditional in line 1, we have that P and P arrow Q is true and Q is false. Okay, let's take a look at the next step. So if P and P arrow Q is true, we know this has to be 1 and 1. So this means that P is going to be true and P arrow Q is going to be true. Okay, so this is line 2. Because P and P arrow Q is true, it follows that P is true and P arrow Q is true by the conjunction. So at this point, P arrow Q is true. There's many different possibilities for this. We know that either P is false or Q is true. But we've already been told that P is true, right, from the previous row. We know that P is true. So it cannot be the case that P is false. Therefore, it must be that Q is true. So at that point, we would get a contradiction. We find Q is false and Q is true, and therefore we know that we cannot force a row that is false. I want to take another method here with a truth tree to show you. Okay, at this point, we already have that P is true and Q is false. So what we can do alternatively is we can put 1s under all the p's and we can put 0s under all the q's because we know p is true and q is false. So we can do this. We can say, okay, p is 1 and q is false. Now, alternatively, let's take a look at this then. P arrow q is supposed to be true, but we find here that P arrow Q is false because we have 1 arrow 0. So this is simultaneously 0 and 1 at the same time. This is impossible. We cannot have that happen. Therefore, our assumption is incorrect, and actually P and P arrow Q has to be true in every single row. So there's two different ways that you can approach this. One way would be filling in the values for P and Q as you find them and finding that you have P arrow Q being true and false at the same time, or using the reasoning that in the conditional, either P is false or Q is true. We know P is true, therefore it has to be the case that Q is true, and then you find a contradiction that way. But this is still the same strategy as finding a contradiction proof for a tautology. So that's it as far as indirect proofs go. It was a very rapid introduction. I know it's a very rapid introduction, but if you work with the truth tables and you keep them on hand, and you draw the truth trees for these, and you try to force a certain truth tree, and you do it visually, you will get this. It's usually, and I'll be honest here, it's usually the fact that there are so many words written down and lots of symbols that makes this tough to comprehend. It's the words, it's the steps, it's the numbers that make it difficult. Try the truth tree method, and every single time you do a step in a truth tree, translate that into words. Worry about the notation and the format of the words later. Get the logic and the process down first. The words come with practice. The process comes with understanding. The process is more important than the words when you first learn. So that's it for proofs. I want to briefly talk about logical equivalence. We're not going to talk about logic laws. I'm showing you them so you have them, but we're not going to use them at this point in the course. So we won't cover them in detail. If we have two well-formed formulas, alpha and beta, they're logically equivalent if the truth tables are the same. So if we have alpha and if we have beta, and if they're the same thing, let's say alpha is like 1, 0, 1, 1. If beta is also 1, 0, 1, 1, then this means that they're equivalent. This means that they're the exact same well-formed formula in terms of truth. So one example is not P and P. Intuitively, these are the same, right? P can either be true or false. Therefore, not P will be false true, and then not P will be true false. Intuitively, these are the same thing. Two negations cancel. But we can prove they're the same by finding a truth table where the columns come out exactly the same. So on question 5 in the assignment, you're asked to fill out a new truth table and find out whether the following WIFs below it are logically equivalent to it. You just have to draw out the truth table for each one of those, and whichever columns match exactly to the down arrow, to the coin dagger, then you have a logical equivalent formula. Now, just to briefly talk about these things, and this is just extra information for you, not being tested on this stuff, but I think it's really interesting. The reason why set theory and propositional logic are so tightly related is because these both stem from things called Boolean algebra. In other words, the algebras of 1s and 0s. Now, when you have sets, you talk about membership. When you talk about logic, you talk about truth. But in reality, they're represented almost exactly the same. The rules are almost exactly the same. It's just the meaning behind them that's different. So for example, in set theory, the complement is similar to the negation. The intersection works the same way as and. The union works the same way as or. Our universe and our empty set is really just the same thing as a tautology and a contradiction. A universe has all the objects. A tautology has all truth. The empty set has nothing in it. The contradiction has no truths. It's all lie. Well, it's all false. A subset of B. This is the same thing as alpha arrow beta. The subset and the arrow are also very tightly related. So, it's no coincidence then that if we were to look at the laws, they come out almost exactly the same. There are two extra ones, well, 3 extra ones that we have compared to set theory. But again, we're not really going to work with these at this point. But if you were to do a logic proof with logic laws, you would be able to do it immediately because it works the same way as set theory. You just have to get used to the new notation. So if we did an example proof, you could go through step by step. This is all just optional for you for your information. You could prove this. But one more thing I want to talk about, just because this is really interesting with logical equivalence, is that in our logic, we use negation, and, or, if then, if and only if, and we've also talked about exclusive or. We do not need all of those. We could have a system with just or and not, and we could still express everything. So for instance, instead of writing P arrow Q, we could just write not P or Q. Instead of writing P and Q, we could just write not P or not Q. Instead of writing P if and only if Q, we could instead just write not P or Q, or not Q or P. Now, as you can see, if we were to translate English like this, it wouldn't be very accurate. It wouldn't represent it well. So we don't use just 2 operators because of that. It's much more convenient to use 5 operators than to use these long-winded equivalents. So we can do the negation and or we can use negation and the arrow, or we could have just the negation and. So if we use negation and the arrow, P or Q could be represented as not P, then Q. P and Q could be not P, then not Q. P if and only if Q could be not. If P arrow Q, then not Q arrow P. So we could use this system if we wanted to. In fact, we could use just the arrow if we want. If we use the contradiction as an atomic statement, we don't even need to have negation in our system. We can just do everything with the arrow. So we could do not P as P arrow contradiction. So if P, then it's false. P or Q. We could do P arrow false arrow Q. That could represent P or Q. P and Q could be if P, then if Q, then false, then all false. And P if and only if Q could be P, then Q, then Q, then P, then false, then false. So we don't do this because it's ridiculous for translating English, but it's just a really cool fact. In fact, actually, if you work in mathematical logic, philosophical logic, and you work with like the meta theory, the real proofs behind the scenes of how all this stuff works, you might actually want to use a system that only has the arrow, because that makes all of the backend stuff easier to prove. Because instead of showing that things work for the arrow, the negation, conjunction, disjunction, biconditional, instead of having to show that it works for 5 different things, if the system only has an arrow in it, you just have to show that it works for 1 operator. So in this course, we're not going to use that. Like, that's not part of the scope of the course at all. But in later philosophy courses, if you like logic and you want to take courses like Phil 110, Phil 310, Phil 314, Phil 315, then you might encounter this eventually. And you'll find that the fewer operators you have, the easier it is to work with the system. It's just when we think about it linguistically and we translate things in English into logic, we want all the operators that we have because they translate nicely. Anyways, that's it for the video this week. There's just one quick thing on proofs. There's a couple of proofs on your assignment. On the assignment with your proofs, I am going to be very lenient marking them because it's the first time you're doing them, but you will see one on test 3. So make sure when you do the proof, you look at the feedback and you try to correct any misconceptions you have as soon as you can. So if there's any questions, email me or post on the discussion board, and I'll get to you when I can.